The last item we're going to discuss in this unit is sensitivity. So generally we can define sensitivity as the degree to which changes in system parameter or parameters are going to affect the system transfer functions and ultimately thereby the system performance. And so we can put this into an equation if we consider the sensitivity of some function, some transfer function f. So sensitivity of transfer function f to changes in some parameter p. Okay, so we could write that sensitivity as sensitivity of f colon p, so that's the sensitivity of f based on changes in p. And so we're going to write this as the limit as changes in our parameter p go to 0 of, and now I'm going to have the quotient of our two fractional changes. So in the numerator, I'm going to have a fractional change in f over, our fractional change in f is a change in f over our original f value. And in the denominator, we have a fractional change in p. So this is the change in p over our original p value. So again, let's just note that those are fractional changes. And so basically we're saying as changes in that parameter p are getting really small, how much is our f changing with respect to how much the p is changing. And so in order to make that equation a little easier to use, what we can do is sort of rearrange that so we just have one term in the numerator and one term in the denominator. So we can say the sensitivity of f with respect to p is equal to the limit as that delta p is going to 0 of p delta f divided by f delta p. And so now we're kind of going to split these parts up and get rid of that limit and our deltas, so we can say the sensitivity of f with respect to p is equal to, so we're going to have p divided by f out front, so that's just going to be a fraction, and then the limit as that delta p is going to 0 of the change in f over the change in p, we're going to change that to the partial derivative of f with respect to p. And again, keep in mind that p is just some general parameter. So I don't necessarily have a good mechanical analogy here, but if we're talking about circuits, maybe we have some amplifier circuit. So amplifier circuit, and our transfer function that we're interested in would be our gain. And so typically we'll represent our gain with A. And one of the common parameters that will vary is our common emitter current gain, or beta. So in this case, we could then have the sensitivity of our gain with respect to beta. I'm sure there are similar mechanical analogies, it's just that I'm not familiar with them at the moment. So ideally, we want to have 0 sensitivity. So in an ideal world, no matter how much our parameters are changing, we wouldn't have any change in our system performance. Of course, that's not reality, so we do need to account for this in several cases. And so we're going to look at an example in the next video showing how we do that. So ideally, we want our system to have 0 sensitivity. So ideal, 0 sensitivity. One other thing to note too is we've sort of glossed over some of the benefits of feedback, but in general, our feedback is going to reduce our system sensitivity. So feedback generally reduces system sensitivity. And to be specific, let's just say to parameter changes. And so going back to sort of our electrical analogy up here, and this is something that those of you who are an electrical engineer, we're going to talk about in more detail in a later class, is when we incorporate feedback, we have a trade-off. So we end up reducing our gain, but we also increase our stability, and so we're not going to be as sensitive to changes in some of the parameters like beta.